mass defect of a nucleus. Energy is given out when nucleons come together to form a nucleus. So protons and neutrons can form a nucleus, and also energy will be given out. Using the mass-energy equation, we therefore know that a decrease in the energy of the nucleus means a decrease in its mass. So from our equation stating that energy E is equal to mass m times the speed of light squared, a decrease in energy means a decrease in mass. As a result, the mass of the nucleus is less than the total mass of the separated nucleons. So if we found the mass of the nucleus and compared it to the total mass of the nucleons that make it up, we would find that the mass of the nucleus is less than the total mass of the nucleons. The difference between the total mass of the separate nucleons and the mass of the nucleus is known as the mass defect. The mass defect delta M is equal to the total mass of the nucleons minus the mass of the nucleus. We can find the number of neutrons in a nucleus given its nucleon number and proton number. Remember the notation we use has nucleon number at the top and proton number at the bottom. And the number of neutrons is equal to A minus Z. Using the number of protons and neutrons and their corresponding masses, we can find the total mass of the nucleons. The total mass is equal to the proton number Z times the mass of a proton plus the number of neutrons, which is A minus Z, times the mass of a neutron. The mass of the nucleus is subtracted from this sum to calculate the mass defect. So we can write out our formula for the mass defect as delta M equals Z times the mass of a proton plus A minus Z times the mass of a neutron, which makes up the total mass of the nucleons making up the nucleus, minus the mass of the nucleus. We're going to learn about a type of energy called the binding energy. We already know that nucleons within a nucleus are held together by the strong nuclear force. The strong nuclear force acts to keep the nucleus together. If there was no strong nuclear force, the nucleus would fly apart due to the repulsive force between positively charged protons. In order to remove a nucleon from the nucleus, we must do work against the strong nuclear force. The strong nuclear force will act to pull the nucleon back towards the nucleus. So in order to separate this proton from the nucleus, work must be done against the strong nuclear force. And because of this work done, energy is required to separate a nucleus into its constituent neutrons and protons. We call this the binding energy. So to separate the nucleus out into all its different nucleons, the energy needed is called the binding energy. The binding energy of a nucleus is the energy required to separate the nucleus into its constituent protons and neutrons. Equivalently, we can say that it is the energy that will be given out when the individual nucleons come together to form a nucleus. So if we have a certain number of protons and neutrons, and we bring them all together to form a nucleus, the energy given out in this process is equal to the binding energy.
Now this is a binding energy per nucleon graph. And this is a graph that you can construct using the entire periodic table by plotting the number of nucleons for each element on the x-axis. So that would be the mass number, right? The number of protons and neutrons. And then the average binding energy per nucleon on the y-axis. So if we take something like hydrogen, or an isotope of hydrogen in its simplest form, which is 1 proton, you would put 1 on here, and you would find out the binding energy and plot it. Very small nuclei are very unstable. They undergo nuclear fusion to become more stable. So if we go back to this idea that the less energy, the more likely it is to fuse or to undergo fission, then what you've got here are the small nucleons, things like hydrogen, isotopes of hydrogen, because you've got hydrogen which is 1 proton, but you could have 1 proton, 1 neutron, 1 proton, 2 neutrons, etc. So they would go here, and they have a very low binding energy per nucleon. So therefore they are likely to fuse. Well, likely. You'd need a ridiculously powerful solar reactor. But they are, at least it will happen. Here we have larger nuclei. Things like lithium, helium. Helium's your next one here. Lithium, carbon, nitrogen. As we increase the number of nucleons, the amount of binding energy increases, and that means that it's less likely to undergo a reaction like fission and fusion. Now, iron is the most stable nucleus, so this is a really, really important feature. Iron is at the top of this curve because iron is the most stable element. And then as we get bigger than that, then we start to go down again, and these become less stable. And yes, now we're on the side of the graph where we approach areas of fission. Larger nuclei are less stable. They undergo nuclear fission this time to become more stable.